Well, good afternoon, ladies and gentlemen. I'm Dale Carlson. I'm a technical advisor for the United States Air Force in propulsion. It's a pleasure to be here today. I want to tell you that when I was approached by Larry about this to speak at an our sponsored event, I went to my manager and he said, well, geez, they're taking one of the oldest senior executives in the U.S. Air Force to come and speak at a event for the U.S. Navy. What does that say about the Navy? They don't have anybody to speak? So it was a rather humorous moment that I didn't share with Larry, but I thought I would share with you today. But no, in all seriousness, look, this is big stuff. I stand up here today representing the U.S. Air Force, but really I am technical advisor, which touches all of the armed services. Work very closely with our Navy and Army counterparts in aviation. I have broad responsibility for both intelligence, special projects, future strategic policy guidance in terms of propulsion, and more important thing of all that I do is sustainment of current and fielded systems, which for the men and women in uniform for both the U.S. Military and our allies in the room, a heartfelt thank you for all that you do. I tell you, it is awe-inspiring to support the young men and women who are in the fight with propulsion solutions for them that make sure that they come home safe. And thanks for all you do. So look, the title of my talk today is The Golden Age of Propulsion, and what I want to do here is sort of provide a framework within which to look at the broader context of the impact of Tizard and Whittle. It is more than just the singular technology set that was brought over and ultimately matured, at least for the U.S., in terms of the GE offering. Golden Age is, you know, there are many definitions for it, but the singular human event really distinguishes a golden age, and propulsion's had many of them. And what I want to set up here is sort of from the start. I'm going to talk a little bit about the Wright brothers. I'm going to talk about the World War II efforts of what we're here today for. I'm going to get off the stage with some thoughts and try to put it in context and bring it back around as to what sort of drove jet engines in the first place and why it's still meaningful today in terms of potentially getting into the fight globally in the future. So look, coming from Wright-Patterson Air Force Base, everybody wants to talk about the Wright brothers, and you know they get their due, but I want to talk about the first, if you will, airframe power plant mechanic. This gentleman, Charles Taylor, because I always like the backstories of technology. As somebody who has been in industry, and I was introduced earlier as having had a career at General Electric, in full disclosure, yes I did. I obviously had to fully redact myself from all my financial holdings and considerations when I came to the US government and have done so. I don't speak for GE anymore. I'm totally agnostic relative to the industry. I'm here to represent the US Air Force and the DOD and not a company. So just rest assured that's not what I'm here for. But look, this guy was interesting because the power plants that were available at the time were heavy. That is, their power to weight ratio was way too heavy for what the Wright brothers needed to go fly. So this guy's my hero because he was the first power plant mechanic. You know, he really enabled reciprocating engine technology to power essentially all of the fleets up to the time of World War II were all reciprocating engine based. And for those of you who wonder what a reciprocating engine is, it's that thing that goes round and around in your cars for the most part, wankles notwithstanding. But reciprocating engines are very efficient. You know, Otto cycle and other thermodynamic cycles, they're just high efficiency, but they're relatively poor in what I call power to weight to volume. And I want to just give a little context to this and a little propulsion background as to why is it important that we have jet engines today. So I mentioned power to weight to volume, and what I've done here is I've put two pictures, 220,000 equivalent horsepower GE90 on my right, your left, with a gentleman standing in front of it, and a $100,000 conventional reciprocating power plant over there where there's a person standing on the second gangway on that thing, if you can see it. So look, you get it right away, okay? 220,000 horsepower in that versus 100,000 horsepower in that thing over there. That's a big difference in power to weight to volume. Now, the part that you don't understand, unless you design propulsion systems, is that power plants, turbine power plants, are the most difficult thing to design in the world, man-made. Nuclear power plants, nuclear bombs are easy compared to propulsion. So I want you to just take a mental check of the number of nuclear powers versus, count them up in the world today, versus the number of countries who have indigenous capability to design jet engines. And I'm standing in front of you today telling you, as someone who owned the Asia Pacific Rim technology strategy for General Electric, that there are other countries want entry into this, but propulsion systems are extremely tough. And let me just normalize this discussion by this. Think about designing a material system that is the thickness of a paperclip that you suspend a Volkswagen from it. That's the kind of material system and capability you need to hold on to a turbine blade on a rim that's spinning at 14,000 RPM. So these are incredibly difficult machines to design. And I think the genius that I contend will come out that from Tizard and Widdle is that they were the first, if you will, systems enablers of being able to go do this and demonstrate it. So let's talk a little bit about this gentleman, Sir Frank Whittle. I always like the backstories because despite success, despite what systems or processes are in place for success, it always comes down to the people. And this gentleman, and I talked to a lot of the historians out at Wright Pat who helped to write the IGTI book on the history of the jet engine in the United States, which is the source of much of this material. And there's a number of people who are still alive who knew both von Oheim and Widdle, believe it or not. Getting ready to retire, most of them, but there are still a number of them there. And I sit in the office where von Oheim sat, by the way, which is rather intimidating at times. But look, this guy Whittle was an interesting character. He was the I contend, the Thomas Edison of aircraft gas turbines. You know, he started off as an RAF cadet with a vision of the possibilities of jet propulsion in 1928. His first patent application was roughly around 1930 on using a gas turbine. He formed Power Jets in roughly 1936 with 2,000 pounds of then worth working capital. And he met Henry Tizard in March of 1936, who sponsored a report that I paraphrased and I extracted from on a committee that the following statement, I'm going to read it to you, because I think it's important to put this whole thing in context. It says, in its present form, the proposed jet propulsion system cannot compete with a conventional power plant where economical flight is demanded. It is of value only for the special purposes such as the sustainment of high speed or high altitude for a short time. But despite that negative report, Tizard's subcommittee issued a small contract to Power Jets. Now, Power Jets was not flush with cash, all right? They needed the sponsorship that Tizard and his committee drove. So that got them going. And so we all know how important it is for the government to be involved in the sponsoring R&D and S&T, and we'll talk a little bit about that later. So look, in the propulsion community, he was not a made man. Now, he was in the Royal Air Force, but he was not a made man in the propulsion community. And he had difficulties getting professional acceptance of his approach and his technology needed for high-speed flight. I can tell you, as somebody who had strategic responsibility at a corporation, the difficulties he experienced are not unlike those that those in a strategic planning position or in industry or in government are in today. You're always bucking, if you will, the established powers whenever you seek to introduce or change the S-curve of innovation in a corporation or in a government. So his experiences are not unlike those who are leaders today. He had a very, frankly, autocratic management style. He liked to micromanage everything, and his health suffered as a result, by the way. But what I particularly admire about Widdle, as somebody who's put engines in the sky and gone through an engine development cycle, as he did it typically with one engine with multiple rebuilds. Today, we do 4 to 10 engines, test engines, development assets to go and qualify a power plant. He did it with one, which made it particularly impressive to me as someone as a systems engineer who had blown engines up in development. To be able to do what he did with one was quite impressive. So we know about the successes. July 1939, the Air Ministry contracted power jets for the Whittle flight engine W1 that went in the Gloucester aircraft. We all know about that. The first flight occurred, started the jet age for the Allies, but it really also spoke to the beginning of the end for power jets. Whittle, in his micromanagement style and his autocratic style, wanted to be the prime system integrator, not only for the engine development, but he wanted to also take the responsibility for the integration of the engine into the airframe. So interestingly enough, the model where one splits, if you will, qualification of the power plant, as we do today with the FAA certification of the power plant, versus the certification of the aircraft, really started because the British government decided that Whittle was not going to be the prime integrator, and that sort of set the framework for which modern qualification of jet engines and airframes has followed. And he even lost his authority over production engines built by subcontractors, so you can imagine what a blow that might have been for somebody who loved control. October 1943, the Ministry of Aircraft Production notifies Whittle that Power Jets Limited will be nationalized. The tyranny of the tactical doomed Whittle's plans. Now, the tyranny of the tactical is something that we all deal with because in the Department of Defense, we all plan against the FIDEP. That's how we run our business. That's the financial model. And that's the tactical, if you will, framework within which we have to run our programs. So it was a wartime. The Edison development model was not going to work, all right? And clearly, Whittle could not withstand the pressure of the British aircraft establishment to absorb his company. He could not stand up to it and lost. And it's well documented in the source reference that I spoke of earlier. But look, despite all of this, and despite the transference of much of the technology over to the US through the Tizard Mission and subsequent transfer of real drawings and real engines, there was a lot of organic British development that went on in propulsion in World War II. It wasn't strictly the US alone developing the technology. There was a lot of organic development in Great Britain. As a result of what happened with Widdle, it certainly made Rolls-Royce and General Electric aeroturbine propulsion leaders. Pratt Whitney came in much later. Pratt Whitney had the enviable position, we'll talk about in a little bit, along with Curtiss Wright, as being the lead manufacturers of radial piston-driven propulsion for the war effort. But Rolls-Royce and then General Electric, which we'll talk about in a little bit, as aeroturbine propulsion leaders, along with today, of course, Pratt Whitney. And the nice thing for Frank Whittle is that he was knighted deservedly in 1948. One other thing about Whittle, although he was a visionary, he never spoke of the potential advantages of jet-powered propulsion in commercial aircraft, which is interesting because, in fact, it took about a decade and a half after the war before it really caught on. But when you think about it, going 550 miles an hour is a significant, if you will, yield advantage for an airline versus going 1/2 or 2/3 that speed, because of the number, if you will, in a military term, sorties you can generate, turn rates per day with an asset that you have. So jet engine propulsion is very efficient in terms of managing fleet yield for an airliner, which is one of the other reasons why jet engines are so ubiquitous today. Now I want to talk about the US and the Whittle engine because I think it's important to sort of set the framework within which to look at where the US stood going into World War II. They clearly were behind by roughly 5 years. Compared to the rest of the world, they had significant strengths through turbocharging technology that GE had. They had a world-class materials portfolio, things like Hastelloy and other alloys, high-temperature alloys. The US was a world leader in materials. I can tell you as a jet engine designer that the best way to manage thermal pressure and mechanical forces and the gradients thereof in a jet engine is through materials. If you've got a higher temperature, higher strength material system, it solves a lot of your ills, okay? And the US also led the world in building commercial airliners. Now, within the geography of the United States, the US needed aircraft with range, whereas the European combatants needed aircraft with emphasis on performance. One thing you know about radial engines is that they have great fuel efficiency as compared on a straight fuel efficiency basis to a jet engine. So range and low fuel usage says go radial. You know, going back and thinking about the power density that I spoke of earlier, that says go jet engine. And we're going to talk about the synergy of the two a little bit later. So US aircraft going into World War II were superior in reliability and range. And piston engines and first generation turboprops were the way we did things. But the US was clearly behind Europe in understanding high-speed aerodynamic phenomena, where significant compressibility effects have to be considered and modeled, axial compression systems, where you stack literally rotor behind rotor to increase pressure, and the US never held the absolute speed records in any of the aero classes in the 1930s. That was strictly the domain of the Europeans. So the US went into the war with a mixed portfolio of capabilities, but clearly propulsion was not one of them. So General Henry Hap Arnold made a trip in 1941 to England, observed a Whittle engine in a Gloucester aircraft, and formed a working group that facilitated transfer of the British gas turbine technology to the US. So as my distinguished colleague mentioned earlier, that the first set of drawings was incomplete as a result of the Tizard mission. We needed a much more complete set of drawings. In fact, a power plant was indeed brought over, because I can tell you as an engine aircraft propulsion system designer, frankly, drawings are useless to design a jet engine. So I can give you a set of drawings and I can give you both the design practices, and you still can't make a jet engine, because it's a matter of systems integration, and we'll talk about that a little bit later. So, in 1941, General Arnold revealed the drawings of this British jet propulsion plant to GE executives, and GE was selected because, frankly, Pratt & Whitney and Curtiss Wright were constrained to build at full capacity engines for the military aircraft. So GE was the best US company in turbomachinery design, and perhaps taking a cue from Whittle's problems, he feared opposition to emerging propulsion technology should he try to get the more established players to take on this new way of doing things. And I can tell you that when you introduce a new technology, I can tell you from experience, you're better to go with a startup than trying to get an established company to get it going. I can tell you that from experience. So GE's goal was to take this engine and design an automatic control system, was to use turbo supercharger experience to prove the mechanical design, that is the high, if you will, RPM mechanical design, that is take a centrifugal loading better into consideration. Oddly though, they were not allowed to change the performance parameters of the Widdle engine. That is, horsepower had to stay the same. So you might ask, well, why is that? Because we as jet engine designers love to increase performance at the detriment of what? All of the illities, reliability, maintainability, everything else. So wisely, actually, they insisted, General Arnold and his team insisted that you were not to increase the horsepower, which as a side note, the component improvement programs that are funded within the armed services today are focused strictly on safety and the illities and not on component performance improvements. So that model has stuck within the DoD for year-over-year funded upgrades to propulsion systems. So then General Electric and the 1A turbojet, in October 1941, the drawings, the W1X, WTB arrive in Lynn. In a very short turnaround time, April of 42, the 1A engine was tested for the first time. Great job, but you know, as I mentioned earlier, GE really had the luxury of build them and bust them. They had numerous assets. Widdle had no such luxury. But the Army Air Force did not consider GE as a developer of jet engines and not as a producer. So believe it or not, the J-33, which was the ultimate evolution, if you will, and I won't go through the entire history, the J-33 was sort of the final reincarnation of the jet engine from the Whittle design, and the US government passed that on to the Allison division of General Motors in October of 1945, and the J-33A-21 was the first turbojet produced for commercial use. In fact, Allison produced those, I believe, until the late 50s for commercial use. So GE and the whole evolution of GE after this I won't go into today, but initially they were just considered a development shop. Get it to TRL-6 and get out of the way in today's language. So look, I want to give you a perspective on Whittle and Tizard that I think is important to keep in mind. So clearly Whittle reset the innovation S-curve for propulsion when it comes to the West. Now, he's different than von Ohain because von Ohain had a very good support structure. He had a very strong cadre of scientists and technologies that supported him and helped fund him right from the beginning. Power jets had a struggle to attract working capital to get going. So what I like about Widdle is really is the first self-made turbine propulsion systems engineer. He was able to take all of the pieces, balance the pressure, thermal, and mechanical forces, and get it into the box so it can work. I want you to go back and think about what I said earlier. There's more nuclear powers than there are propulsion powers in the world because, and I said, I can give you the drawings, but you still can't make a jet engine. Because systems integration of all the pieces, knowing how to program the control system, know how to do what when, performance, operability, control, surge-free performance, all of the things that you have to do, aeromechanics, materials, everything else that goes on in the jet engine, that's systems engineering. And that's where I believe the greatest contribution came from, because although Tizard tactically was the first official government sponsor of Whittle's work, what really came out of the whole Tizard mission, if you will, was the ability to transfer the concepts of operations research, which ultimately became systems engineering, which if you go back to the history of the Cold War, the thing that really differentiated the West versus the Soviet Union was the ability to do large-scale systems integration successfully. So the fact that the magnetron brought radar, which brought fire control, which brought integrated, if you will, radar capabilities across the dew line, and everything else that occurred as a result of systems of engineering in the West had profound impact on Western leadership for both Britain and the United States, Canada, and our allies. So for a jet engine designer such as myself, I tip my hat to those who brought the concepts of operations research over, along with everything else that came in the briefcase on the Tizard mission. So look, what about today? So I said golden age of propulsion, is this one of them? I asked that question at the beginning. So commercial engine, commercial forecast globally, roughly 30,000 new aircraft deliveries worth about $4.4 trillion between 2013 and 2032. Most of that growth in the Asia Pacific area. That is a huge market. Right now, we're in an unmatched time of parallel developments in what I call the trinity of propulsion. Engine architectures and cycles, variable cycle engines, intercooled engines, geared turbofans, on and on it goes. Materials, non-metallics. When I first started as an engineer, there were 3 cardinal rules of design. Design within your experience base, design with tools you know, and always design with metals. Today, that's no longer true, all right? Non-organic composites, ceramic matrix composites, very advanced exotic material systems are just standard work now within propulsion. Manufacturing, additive manufacturing, you've all heard of it. It is making its way into the propulsion design and manufacturing space. It will fundamentally change the entire engineering design paradigm. The way I was taught as an engineer will not be the way that engineers are taught in 2025. Additive manufacturing will fundamentally change engineering forever. Propulsion design and integration are still the province of the few. There are aspiring players. India wants it, China wants it, even Turkey has talked to me when I was deployed at GE about developing their own indigenous capability. I'll say one thing about this and the US government sponsorship of propulsion. So a sheik came to speak about developing an indigenous propulsion capability in a Middle East country some years ago to us when I was in industry. And I remember the CEO telling him, you don't want to do that. that turns billionaires into millionaires. And the fact of the matter is, if you look at the launch of a new centerline engine from any of the large original equipment manufacturers, you're talking 2, 3, 4 billion and up investment with payback periods that can be 15 or 20 years. You think about that if you're an angel funder or something like that. It's a business model most people just don't get. Now, there was a question answered earlier about intellectual property, and I really want to stick my hand up because I used to own intellectual property strategy when I was in industry. One of the things that I think is going to be the most disturbing in terms of potentially emulating the Tizard model of cooperation is what I see as the ominous trends in intellectual property protection linked with technology advances as governments pull back from funding R&D and S&T on a real dollar basis. What's happening is industry's picking up more and more of the load. Globally, what you see is, in fact, that the World Trade Organization rules on IP, while necessary, certainly aren't sufficient. It is becoming much, much harder now to negotiate with companies on data rights. Companies are becoming far more protective. There's something known as fast-tracked IP policy that the Patent Office in the United States has instituted, where your patent doesn't get the cold hard light of day scrubbed until it's issued. So there are huge intellectual property trends that are taking place that will probably make future cooperation much more difficult. So look, I talked about the Whittle engine a little bit, that it had this high specific thrust, if you will, high power density, but it has relatively poor fuel efficiency. After World War II, the jet engine that you see at the airport now with the big fan in front, that's what's known as a two-stream turbofan. So you get the combination of thermal efficiency from the core, from like the Whittle engine, plus with a fan that drives air around the outside. That gives you high propulsive efficiency, but it reduces specific thrust, if you will. But today, what I contend is this is a golden era for variable mission capability. You need a variable cycle engine, one that combines the best attributes of both high specific thrust and high propulsive efficiency to allow you to independently modulate mass flow and thrust, which no engine heretofore has been able to do. Usually when a pilot moves the throttle, you're directly changing the mass flow through the engine, and then the thrust changes. Now with a variable cycle engine, you can independently modulate thrust and mass flow through an engine. And the good news is pilots or former pilots, you don't get an extra stick to play with. It's still the same stick. It's all programmed through the automatic control. So you get both range and high performance in the one system. So if you think about what drove propulsion developments in Europe, the jet engine, was this need for high performance. Range was a need for the United States because of the spread of the geography. Now you can get it in one system, which when you think about projecting power over the globe with limited tanker support becomes much more important. So look, we still work very closely with our British and Canadian and Australian and New Zealand allies. We have a number of programs, not going into detail here, NATO Collaboration, the TTCP, which has been mentioned earlier. Within my wheelhouse, that is mostly in materials and aerospace systems, and obviously we have a strong and ongoing series of bilateral agreements that we support through the laboratories as well as in the Life Cycle Management Center at the U.S. Air Force. So look, Tizard and Widdle really helped spawn an unprecedented portfolio of propulsion-related technology developments and a vibrant industry. If you look at, where the U.S. really makes its money in terms of exports, it's in aerospace. And a lot of that, plain flat airplanes and propulsion systems that are sold globally. Going forward, collaboration demands the following, in my view. Continue to develop a broad technology bandwidth. One of the things about technology strategy is you don't know which technology is going to stick in the future, so you got to have breadth, and you got to have a certain depth, that is a certain maturity, to go with it, and adjacencies matter. And what I mean by adjacencies is, okay, I'm an aero guy, I'm a mechanical designer. Adjacencies means design with electrons, things that going to the more electric aircraft, the hybrid type engines, that is directly applicable in propulsion just like it is in automobiles. And that is an area that no one can stand to be in second place in. Resources to renew our technology DNA, going back to the FIDUP discussion. One of the toughest things about my job is giving advice about what the potential adversaries and breakthrough technologies might be in 10 or 15 years and how to get ready for them. The most frustrating thing is to go in and see things that I know are going to make a difference are shelved at TRL 2 or 3 because they are too risky. Well, by the TRL grading scale at 2 or 3, they are risky because they have not been matured. Where I know that there are adversaries, potential adversaries around the world funding things that will make a difference in the future. So you have to have the right balance of tactical investment and strategic investment, and we all do. And manage our technology portfolios. I spoke about intellectual property. This tends to and is becoming one of my biggest concerns because I think that companies are becoming much more aggressive in asserting data rights over things that they've developed under their own nickel or took at an early TRL from government sponsorship, put their own monies in and declared them their own. So I think we as a collective entity are going to have a much more holistic view of data rights when it comes to acquisition strategy going forward. However, given all that, I think we stand at the dawn of a new golden age of propulsion. You're never done. This isn't a fully mature industry. There's always room for innovation. And I hope and I desire young people to get into it because it is an exciting place to be an engineer. Those are my thoughts. Thank you very much for your time and attention.